Yeah. So this is the more complex one. You have to do the Hilbert transform and then you combine them together and send. Okay. Yeah. Another one is you just generate the DSP-SC. Actually, this part is DSP-SC, and then you filter it. Okay. So there are two ways to generate the DSP-SC. Okay. So this is using these equations where you need to do the Hilbert transform. This one is this part will generate DSP-SC. After that, you filter out one of the sideband, you will get the single sideband. Okay, yeah. Okay, the process are the same. Okay, let me see, sorry. Yeah, okay. So the process are the same. So that's why I will use this example to show the step. Okay, so again, I think it's the same MT. Okay, it's the same MT as the previous two examples. And then again, it's the same CT. Okay, the same MT, the same CT. Okay, so again, this is the equations for the single sideband. So cos, so this is the same. So it's just MT, CT, minus plus AC. So cos, the Hilbert transform is sine. Okay, so both become sine. Okay, yeah. So and then it depends. You want the upper sideband or the lower sideband. If upper sideband, you take the minus sign. If lower sideband, you take the plus sign. So in this example, we show both. Okay, yeah. So that's why. Can you do this? And you will get this. Okay. So this is cos A cos B. So it's half cos A plus B plus half cos A minus B. So what is sin A sin B? Sin A sin B. So it's half. What? I forgot already. Is this sin sin? Sin sin, right? Sin A plus B plus half sin A minus B. Am I right?
Yes.
Yeah. Okay. Yeah. Yeah. Yes. So can you do it now? How can you get from here to become this one? Yeah, you say yes or no.
Do we have to do this now? Do we have to do this now? Actually.
Okay, got it? Not yet. Okay, yeah, so your friend got it already. If you cannot understand, ask him. Okay? So that's why you get this already. So that is the speed that you need. So benchmark your friend here. So yeah. So you can see if you take this and take the Fourier transform, you will get this. Okay, so I believe here you can plot the spectrums. So you plot the spectrums. So this FC plus FM. So this negative FC, negative FM. You have two impulses. Okay, yeah. So you can see we only have USB. And what is this? AC over 2. Okay, so if you plot the spectrum for USB, you get this. If you plot the spectrum for LSB, you will get the other two. That is here and here. Negative FC plus FM, FC minus FM. Okay, AC over 2, AC over 2. So you can compare with, I think that is example, this one, okay? Example 1. So it's the same, actually it's the same function you can see, but that one we A, so it's the same. So that's why you get DSP-SC, you get 4, now you get only 2, okay? And either you get USB or LSB. Okay, so I didn't plot the spectrum, you can draw the spectrums, okay? Yeah. So that's how we obtain a single sideband. So yeah, all those we see this as a single sideband, okay? So the advantage is that the bandwidth is reduced back to W. Okay, so the bandwidth of the modulated signal UT is the same as the message signal MT. Okay, if you use a single sideband. So is there a carrier there? Is there a carrier in your spectrums? No carrier also. So that's why this is still suppressed carrier. So that's why for the demodulations, okay, so not yet, not yet, is it yet? Okay, yeah, I didn't mention. So for the demodulations, you have the same problem as DSP-SC. You need a synchronous demodulator, okay? You need a synchronous demodulator, here, okay? So you still need a synchronous demodulator or a phase coherence demodulator. Okay, so how to demodulate is the same. Okay, so you must just multiply the received signal with cos 2 pi FCT plus phi. Okay, so it's exactly the same as DSP-SC for the demodulations. Okay, so yeah, if you manipulate here, you will get this one. Okay, again, what you want is you only need one of this signal. So you can see there's MT here. That is Hilbert transform of MT here, and then the double frequency term. Double frequency term means 2FC, 4FC, and so on. Okay, so it's the higher terms. So as usual, we will not recover from the double frequency, and also we do not need to recover from here. Basically, we just need to recover from here. Am I right? Okay, so we can just recover from here. What we do is we just need a low pass filter. But no matter how, when you use a low pass filter, you get these two terms. Okay, so you still get these two terms. Yeah. So yeah, so that's why if we can select phi carefully, if phi equal to 0, if phi equal to 0, cos 0 you get 1, sin 0 you get 0. So that's why this will disappear. Right? So you only have this part, and it's ACMT over 2. So it's exactly the same problems that we face in DSP-SC. Okay? If you have a synchronized or phase coherent demodulator where the phase is 0, then no problems already. It's the same demodulations. Okay? Yeah. So yeah. So that's why, and similarly, another alternative is you use the pilot tone. That means you include CT in the UT. Then you will do that. Okay? Yes. So yeah. The SSP AM is a very attractive models when the bandwidth is limited. So that's why we use single sideband AM in the telephone channel. Okay, so that's why in the telephone channel, one of the very famous problem is what we call clock synchronization. Okay, so that is to synchronize the clock between the transmitter and the receiver in the telephone networks. Okay, so I still remember that is the master project of Dr. Camaro. Okay, yeah, so we study very much the same time. So that was his master project. So it's the clock synchronizations between the transmitter and the receiver in the networks. Okay, yeah. Okay, so yeah, this is the third type. So we have seen 3 types. Okay, 2 type is double sideband. Yeah. And then 2 type is suppressed carrier. Okay, so we have an options not to suppress the carrier or to transmit only single sideband. But every of this method there is a pro and cons. Okay, yeah. So yeah. So that's why we come to this. The last type is a little bit more flexible. Okay, it's a little bit more flexible. Okay, you see when you want to, for example, filter out what we call the one of the sideband, for example. Okay, so you need to design your circuit like this. You need a very perfect band pass filter, or you have a very complex Hilbert transform and so on. Okay, so there's another way. Okay, we can be a little bit relaxed on the requirements of the sideband. Okay, so one of the sideband is complete, another sideband we do not require to be completely eliminated, to be completely removed, so that the circuit that we design can be slightly more relaxed. Okay, so yeah, this type of circuit. Okay, so we use a sideband filter to filter out the sideband, but we know that there's no filter is perfect filter that will filter like this, right? Okay, you study filter. Okay, so a perfect filter is just like this. Okay, but we don't have that kind. Okay, so our filter usually will filter something like this. Okay, so the ideal one is we can filter just like this. Okay, yeah. So to make the design less straight, the requirement is more relaxed. Okay, so that's why we have this vestigial sideband AM. So they allow some leftover of the other sideband, the unwanted sideband, in the circuit, in the output. So this is basically easier to implement. Again, cheaper. Okay, yeah. Whatever you have very strict requirements, you have to do a very complicated hardware to implement that. So if we can relax, that is fine. Okay, and also depends on the type of signal. Okay, depends on the type of signal. Sometimes this type of unwanted leftover, okay, will not affect the system very much. So that's why we will see the vestigial sideband or the VSC, okay, in the video signal. Okay, when we do it with the video. Okay, so how to do that is quite simple. So we just pass through the, again you can see here is USB-SC. So we just pass the USB-SC signal in a sideband filter. Okay, so where the transfer functions of the filter is checked. So this kind of function is just the USB-SC and then convolution with HT. Okay, and if we look at the frequency domains, here is convolutions. When come to the frequency domain, it's just multiply. Okay, so yeah, this one is a times it's a frequency shift, and then multiply with the transfer functions, okay, of the filter. So yeah. Yeah, this is demodulations. Okay, so demodulations is the opposite direction. Is the opposite. So again, you multiply with the same carrier functions, and then you pass through a low pass filter. You will get back the original signal. Sorry. Yeah. Okay, so this is how you will do the demodulations. Okay, so basically these are the 4 types of AM. Okay, 4 types of amplitude modulations. Any questions? Any questions? So what you need here is, first, you remember the equations for different type of AM modulations. Okay? So the first one is very simple, MT, CT. The second type, you need to do the normalizations and then you need to multiply with the modulation index A. So it's 1 plus AMN, then only you multiply with CT. So, and then the third type where you need the Hilbert transform. So that's for the single side band. And the last type is slightly different. Okay, the last type, like the equation you see just now, is involve convolutions. Okay, yeah. So 4 types. So that is the first thing, you get the expression in time domains. The next step, we always need to see the spectrums. So in order to see the spectrums, we need to take the Fourier transform. Okay, so that's where you need to apply the Fourier transform and then look at the table. So then you will get the spectrum. So very often you can plot the spectrum. Okay, you can draw the spectrums and look at the bandwidth. Okay, so the spectrum will let you see the bandwidth. The time domains, you don't see the bandwidth basically. Okay, even you want to determine the bandwidth of the message signal, so you need to convert the message signal from time domain to transform, not convert. You need to transform from time domain to frequency domains. Then you can see the spectrums of the message. And against the spectrums, let's say you have a signal like this is 0, let's say this is the message signal, the spectrum is, the bandwidth is just 1. Okay, because this is FM, this is negative FM, so the bandwidth is just FM. Okay, yeah, so that's how you determine the bandwidth. So that's another part, is to calculate the power. Okay, to look at the power. So yeah, that's all about AM. Okay, so you need to understand these 3 parts. You need to know how to interpret the result. Okay, yeah, so it's not just about calculations. Okay, so that is all about AM. Okay, and this is question 1A in your final exam. Okay, any questions? Okay, good, no questions. Yeah, I don't want to waste time because no time. Okay, so again, try to do some exercise from the textbooks, okay, for you to understand AM better. Okay, yeah. So these are some of the questions that you can do. Okay, we look at the second type. The second type is called angle modulations. So why is angle? Because we are going to change what is inside the sinusoid. Okay, if you look at the function, amplitude is kind of like outside the sinusoid, right? Okay, so now we want to change inside the sinusoid. Okay, so we can either change the frequency or change the phase. Okay, change the frequency or change the phase. But somehow, if you can imagine, okay, changing the phase actually can be translated to changing to of frequency. Okay, so later we will prove that. Okay, so that's why when we study FM and PM, we don't study separately. Okay, because they are very much the same type of manipulations. Later we will see. Okay, but theoretically, FM we change the carrier frequency. Okay, so we change the carrier frequency according to the message signal. So we use MT to change FC. Okay, yeah, and then the phase, the PM we use the MT to change the phase. Okay, the carrier, yeah. So yeah, both FM and PM, we call non-linear modulations. Okay, why non-linear? Because you will see the frequency will change. Okay, so that's why it's a non-linear modulations. AM is a linear modulation. The frequency will not change. It's just the amplitude change. Okay, so that is a linear modulations. So what are the advantages? Okay, what are the advantages? So basically, angle modulations, they have higher degree of noise immunity. So that means better resistant to noise. Because usually noise is affected by amplitude mode. Okay, yeah. So yeah, you see, I talk here, the amplitude is loud, right? So outside further is not. So if I talk, you talk together. So basically, you know, it's the noise affect the AM, okay, more, okay, yeah. Of course, it doesn't mean that the FC, the frequency and the phase cannot be distorted or disturbed. Yes, it can, okay, but mostly it's the amplitude. So that's why basically FM and PM, they have a higher immunity to noise, okay, yeah. And then you will see that the signal will have a constant envelope. Okay, so that you see the amplitude will not affect the quality of the transmissions, because what is changed is the frequency or the phase. So even your signal is louder or you know, larger or smaller amplitude, or the amplitude change, it will not affect the signal. So it's a constant envelope signal we get. Okay, yeah. Yeah. So and then what is the disadvantage? It's more complex to implement, okay, and then it's more difficult to analyze. That means for the demodulations. So basically the demodulation will be much more complex, okay, yeah. And then the bandwidth required is many times more than AM, okay. So just now AM we have W or 2W, right? Okay, so this one you can expect a lot of W. Okay, it's much higher. Okay, and theoretically, you need infinite bandwidth. Okay, theoretically you need infinite bandwidth to implement FM and PM. Okay, but later we will see that how we can reduce the infinite to finite. Okay, but even it's finite, it's still much larger bandwidth required. Okay, so then why we use FM? Then why we still use FM? Basically, the quality is better. Okay? Basically, the quality is better. When you have higher degree to noise or higher immunity degree to noise, the quality will be better. Okay? So we go for quality. Okay? So the others, you know, complex to design and so on, we will solve it. Okay? So that's why we need engineers. Okay. Again, we look at the carrier signal. Okay, so we look at the carrier signal. So again, we have the same carrier signal. So it's always the same. It's still a sinusoid. So yeah, the CT is always this one. So now we include this one. Okay, yeah. So it's always this one. So yeah. After we modulate this one, okay, so we modulate the MT, we will get the UT, okay, so the UT, we can represent UT using these equations, okay, so we can still the FC there, but we see something called delta T, okay, so delta T is a time varying phase. Then you will say, the frequency remains the same, right? The frequency is FC, right? And then just the phase is a time varying phase. That means the phase will change according to time. Okay? You can imagine that delta T is like a random process, because it depends on T, right? Okay? It's definitely a random process. It's a random process that depends on MT. Okay? But don't worry, we are not going to talk about random process here. Okay? We do a systematic mathematical modeling. Okay? So why I can say that, you know, this delta T also represent a change in the frequency. I believe it's very obvious, right? We see a change in the phase. Am I right? It's because it's already mentioned, it's a time varying phase. But we can show that, you know, this delta T actually also affect the frequency. How? Okay. If we look at the instantaneous frequency at a time, we call that Fi. So that is the frequency at certain time. So you can see it's Fc plus this delta T. But this delta T is the differentiation of delta T. Yeah. Why? Because we know that frequency, if we look at, so this is the change of the data. Okay, so let's say it's a rotation. So frequency is how many rotation per second, right? Okay, and the rotation depends on the data. Am I right? Depends on the data. Okay, so we have an equation where F is equal to, sorry. omega is equal to 2 pi f. So this is the angular velocity, okay, or the angular frequency, okay, and yeah. So frequency is equal to omega over 2 pi, and this frequency, this is the angular frequency, right? Omega. So you know that omega is equal to d theta dt, right? It's the change of the angle with respect to time. Okay. So if you substitute this into here, so you will get is 1 over 2 pi d theta dt. So that's why the rate of change of the theta, the rate of change of the phase, okay, multiply with 1 over 2 pi. So that is the change in the frequency. So that is how we have this part. Okay. So this explains why this time varying phase also affect the frequency. Okay. Yeah. So so that's why these equations represent both FM and PM. Okay? So regardless is frequency modulation or phase modulations, we can use these equations to represent the modulated signal. Okay. For PM, it's rather straightforward. So phase modulation is rather straightforward. So this theta t is just a constant value that we call a phase deviation constant, later we'll determine, multiplied by mt. Okay, so if you substitute this directly into here, so yes, you will have a signal where the fc remain and then the theta t will depend on mt only. Okay, yeah. So for fm, okay, so is the phase, is the frequency difference. Is the frequency difference, you can see fi minus fc equal to, or this frequency difference is modulated by the message, or this frequency difference depends on the mt, and again multiply with a constant kf. So the kf is called a frequency deviations constant. Okay, so yeah, in AM we only have the conventional AM, we have a modulation index. Okay, for FM we always have a modulation index. Okay, we always have a modulation index. So later we will relate the modulation index with this. Okay, now we just say, okay, it's multiplied with a constant. Okay, yeah, and the message multiplied with a constant, and then that is equal to theta t, or that is equal to the change or the difference in the frequency. Okay, yeah. So yeah, these are the equations. Okay, yeah. And we from here we know that Fi minus Fc is 1 over 2 pi d theta dt. Okay, so basically from here you can obtain d theta dt is equal to 2 pi multiplied with kf mt. Okay, so if you have mt kf, how you do fm is you need to do this one, differentiations here. Okay, yeah, yeah. So as a summary, if you do fm, okay, if you do pm, it's rather easy. You just take fmt multiply with kp, that is your theta t. Okay. For FM, it's slightly more complex. Okay, so you need to do the integrations of the message signal, multiply with 2 pi kf. That is your theta t. That is how you add here. Okay, yeah. So yeah, basically this is the summary of the equations for angle modulations for both FM and PM. Okay, yeah, slightly more complex. Okay. Okay, we look at this part. If we look at the theta t dt, this is what we get for PM and FM. Okay, so we will notice something that is very interesting. Okay, we represent in here. If you have MT, you integrate, and then you multiply. You can see Kp and 2 pi f is just a constant, right? Okay, yeah, you just multiply a constant. Actually, they are the same. So a FM modulator is equal to an a combination of an integrator with a PM modulator. Okay, yeah, so that will give you a FM. And similarly, a PM modulator is equivalent to the message go through a differentiator, differentiate, and then use a FM modulator. So they are the same. Okay, so this show why, you know, how they are the same. So you can see this is MT. If we take the FM signal, it's like this, right? Okay. If we take the integration of the message signal, if we integrate this, okay, we get this one, and then we use a PM modulator. You can see this signal and this signal exactly the same. Okay. Or you can also look at the differentiations, and then you will also notice that the PM signal and the FM signal will be the same if they go through a differentiator. Okay, so here only show the integrator. Okay, yeah. So yeah. So yeah. How about demodulations? So demodulation of FM signal involves finding the instantaneous frequency. Okay, so it's basically based on here. If you know what is the instantaneous frequency, you minus the carrier frequency. Carrier frequency is known, right? It's just a carrier frequency, it's the sinusoid. So and then you will get the MT straight away. Okay, you will get the MT straight away. Again, this is just a constant. Okay, it only affects the amplitude of KF, so it doesn't matter. The amplitude of MT, it doesn't matter. Okay, so that's why you can see the demodulation is just obtained, or it just calculate what is the instantaneous frequency. Okay, yeah. So yeah, and the demodulation of PM, you just finding the phase. Okay, you're just finding the phase. That means against, you're just finding theta t. After you know theta t, you know what is MT already. Okay, so it's rather straightforward, but the implementation will be difficult. Okay, yeah. So yeah, there's another parameters we call maximum phase deviations. Okay, that means what is the maximum changes in the phase. Okay, yeah, and obviously because the phase depends on the value of MT, right? It depends on MT. So the maximum phase deviations will be equal to the phase deviations constant multiplied with the maximum value of MT. So we still need to find the maximum value of MT. Okay, yeah. And similarly, the maximum frequency deviations is just equal to the frequency deviation constant multiplied with the maximum value of MT. Okay, and against yeah, when we talk about the maximum value of MT, is the maximum of the magnitude. Again, if you have a 3 and -4, the maximum value is 4. Okay, yeah, because the 4 is the magnitude is larger. Okay, yeah. So yeah, so the modulation index. So the modulation index basically is equal to the maximum phase deviations for PM. Okay, or equal to this maximum deviations, maximum frequency deviation divided by the bandwidth. Okay, for FM. So this bandwidth is the bandwidth of the message signal, FM. Okay, so these are all the constant. So that's why sometimes the question will give you the modulation index. So from the modulation index, you need to calculate Kp or Kf, and then substitute into this or these equations. Some question will give you Kp or Kf straight away, then you can apply straight away. Okay? Yeah, very often we will, you know, when it comes to representing FM and PM, we use modulation index. Okay? So that's why we have the A, remember the A? So that is the amplitude AM modulation index. Okay? So for FM and PM, so it's beta P and beta F. So that is the modulation index. Okay? Yeah. Yeah. So I think we just quickly go through these examples. So the MT I think it's the same function again, so it's a cost function. It's used to either frequency modulate or phase modulate the carrier. It's the same carrier. I think this is very much the same signal with the same as example 1. Okay, so that's why I think example 1 is good. So example 1, you know, this signal, we use DSP-SC, we use conventional AM, we use the single sideband, and now we do PM and FM. Okay, yeah. But again, remember, the MT can be any signal. Okay, just that this textbook use a sinusoid. The MT can be any signal. That means I can give you any signal. Okay, as MT. But the carrier is always this sinusoid. Okay, or maybe if the question is naughty, the question will give you a sine function. Or the question will give you a cos function, but insist I add a phase here, plus 45 degree. Okay, yeah, so it's a sinusoid. Okay, it's still a sinusoid. Okay, yeah. Okay, so we perform the modulations. How we perform the modulations? We have MT, we have CT. Okay, so the question didn't give you what is KP and KF, right? I just used. So theta T is just KP multiplied with MT, this one. So and then I put this theta T into this UT equations. Yeah, that's it. Very easy, just like this. Okay, yeah. So you will see, you will ask, okay, can I take Fourier transform of this one and look at the spectrum? Can you do that? Can you do a Fourier transform of this one? Can you look at the table? Can you do Fourier transform of this one? Okay, your friend here is can, okay, very good. You say can, right?
Just shake my head.
Or you just like this, can or cannot? Or you just sleepy? Okay, doesn't matter. Okay, anyone can take a Fourier transform for these functions? You cannot. Okay, so that's why we will stop here. Okay, next week we will look at how we do the Fourier transform. Okay, it's not that straightforward. Okay, so similarly for I think next week we will see that. Not yet finished. Okay.